To learn about the voice recognition subject today. Okay, so go to the week 8, enroll yourself over there, and you can open the voice recognition, voice embeddings, right? Voice recognition and voice embeddings. So there are two ways that we are going to do the voice recognition. The first one is the similar way that we have done for the face recognition, right? So when it's come to face recognition, we did not collect the data and we trained the model using deep learning networks or neural networks. What we have done was we used a deep learning neural network based library to extract the encodings from the faces, and we saved those encodings in a certain matrix places. Then we compared with the face that we are going to check. So that is the embedding based face detection. Why we have done it? Because if we want to create a face recognition based attendance system or unlocking system or whatever, we cannot take multiple images of a person once he joined, and we cannot rerun the training from the scratch. It's going to take a long time and it's going to spoil the GPU hours as well. So to avoid that, we went on the embedding system. So similar to the face recognition system or attendance system or face recognition based authorized system, we have the voice based authorized system as well, right? For example, if you go to like Google Home, right? Let me show some example. YouTube, right? So YouTube Home, go, let's say Google Meet, right? So these Google Mini $50 one, this is a small uh, device to integrate the home automation system where you can say, hey Google, turn on the light, hey Google, turn off the light, what's the temperature and everything. So this has a feature of voice recognition. So when there are 5 members in the home, right? So you go and talk, it will greet you back with your name. Hey Logi, right? Hey Rayu. So whatever the voices that you have trained for, like saved in that thing. So how it knows? It do not do go through an intensive training process. What it requires is it just say, okay, read this sentence. When you set up, it say read this sentence. So you go to this mobile phone, you do the setup, and it say, okay, hello, good morning, hey Google. So a couple of words it will ask you to read. That's all, right? Maybe not more than 10-second clips you have to read. Right? Once you read it, all set to go. So it just record a small part of the audio, right, to recognize your voice. So after that, if you want to set a new person's audio, again the same approach, you go there, it will ask you to read a certain number of phrases. It's like a couple of lines. So once you read, it will save your recordings. After that, whenever you go and say, hey Google or hey Mini, whatever, it will be able to recognize you and greet you by your name, right? This is one example where the voice recognition system is used. And in many other places, higher security zones, what they do is they voice recognition, face recognition, iris recognition. All the three need to be set up to log into a system. So in that case also, they do the voice recognition stuff. But if you ask me, is the voice recognition based authentication system is safer than face recognition and iris recognition? No, it cannot be. Why? Because there are certain technologies now available in AI market where we can deep fake our voice. So I upload one voice of Obama and I type in another column. We will learn that thing in the last part of the lectures. Type over there certain stuff, and what will happen is that type phrase will be talked in the tone of Obama. So it's very hard for you to actually um, identify whether it's Obama is talking or the fake voice is talking. So those kind of tutorials we will do in the last thing. So when it's come to, give me a second. Okay. So when it's come to this voice recognition or voice recognition based authorizing system, similar to the face recognition system, we cannot ask them to talk for hours and record the audio, and we cannot train them. So there should be a very small way of adding their voice into the recognition system. So that is the one that we are going to learn about today, voice recognition based, voice embedding based voice recognition system. Okay, let's go into the tutorial. So once you go open up this tutorial, you will be able to see this Google Colab platform. Please let me know once you're there. Okay. You there? Cool. So now, like there are multiple other places, right? So I have seen a video like fully home automation system. A person wake up and he do all the work by voice commands. Turn on the light, turn off the thing, coffee, everything. Finally, he went to a dental person and removed his tooth and came back home. The system cannot recognize his voice because his way he talks is completely changed, right? So these kind of issues can happen when it's come to the voice recognition system. Of course, even the face is the same. If you met with an accident, the face shape changed, the face recognition system won't take you in, right? So the same thing. So we will do two approaches today because one thing I asked a question during the last lectures. When you want to train an image for emotion recognition system or kind of face recognition system, we have images. So the input actually goes as pixels, right? But the voice is that okay. So the voice is going to be a different story. So it's a time in the x-axis and the audio is the magnitude. How you can put these values into the thing because it's a 2D array, right? Like this. But you have to have a matrix as a pixel when you are going into that. So how we are going to do that using the voice recognition system? Also, we will learn in the deep learning approach. But for some of you, you might find it little harder, the second approach, because it's little too theoretical. You have to do a lot of feature engineering in the audio, but it's good to know. So you don't want to worry too much about that. The first one is very straightforward, embedding based recognition. Second one, we are going to deep dive into deep learning based voice recognition. So that I will just briefly discuss. You can go home and run in your home. If we have time, I will go through that tutorial as well. But the techniques used over here is really, really important because that the same technique that we are going to use for speech recognition, speech synthesis, text to voice to text, everything, right? So the technique is very important that we are going to use over here. Cool. So we also recognize as a human brain, right? When a person call and talk, hey, if Para call me and say, hey, Loki, even from a different number, I'll be able to recognize his voice. How my brain does it. How my brain does it. So there are certain neural network connection perform that task in a different way, but we don't know how we do it, right? So even a person called us and he's having a cold, our brain will be able to recognize, okay, this is the person who is talking, but his voice is not normal. So we ask back, what's happened to your voice? Are you okay? Are you normal? So these things. So our brain does the same thing, the voice recognition system, but nobody knows how we do it, right? But when we want to teach the machine to recognize the voice, definitely we should have data, right? We have to give the data to the machine and the machine should understand, okay, this is the voice of this person. So this is what that we are going to do. Okay. So vector embeddings for audio. So this is the similar approach as we have done for the face recognition system. We have used OpenCV based libraries for face embedding system. Similar to that, we are going to use today a library called Resemblizer, right? Resemblizer. So that means what it does is it extracts certain features from the voice. you put a audio signal. So how my voice varies? So there is a tone for my voice, pitch, right? We call it a scale. The singer sing the pitch, right? So I have a pitch. You have your own pitch, and you have your own pitch. And while I'm talking normally, my voice tone is there, so and my voice variations. So all these things are parameters. So the way I talk, the way I pronounce, everything matters, right? So now it is a deep learning based library Resembler, which is trained to extract all these features, right? For example, if you take your Google Home, your Siri, even Siri, right? So Siri doesn't ask you to talk for 1 hour to record the video. Like it just say hello, hey Siri, certain voices to record. So that's all it needs. It extracts all the important information from your voice. Then when you talk back, what it does, extracted informations are here, and it identify your voice, extract the embeddings, and match with the current vector store you have served. Then what is match over here, and it say hey Logi, what can I do for you, right? So that's how you have an embedding vector store which have extracted features over here. When a person talk, it identify the voice, extract the feature, send through this Resembler library, match with these things as we have done for the face recognition. Then it provides the output. So the same approach we are going to do first. Second approach is little bit different, deep learning one. We will go through that in a little while. So here, if you see what are the features, what are few features that's embedded, there are actually 256 values were extracted from one voice clip. 256 values were extracted using this deep learning library for this embedding space for vector store. Okay. So first what it do is it go through a windowing method. Windowing method is very common in many statistical approaches, right? So in many machine learning. So you have a data, for example, stock price change, right? So everyone look at the window, the traders, right? They predict the next values. So when it's come to that point, what they do is they don't look at the whole window. They see a small window size and see how the pattern varies. And here also they see the small window size. Here also they see the past window size and see how the pattern varies. Based on that, they guess the price might go up or low, right? It's all based on the window based selection. They don't take the whole window and see window by window. Okay, in this window, when this trend happens, next day it went high. So in this window, these things happen, next day it went low. So here we are having the same scenario, so it might go high. So that's how it works. Even the machine learning, we do the same thing. So in the voice, what we do, window by window, we are going to move and analyze certain features. And short-term Fourier transform. How many of you have heard about this word, Fourier transform? So luckily we have it in engineering. Otherwise, there is no audio engineering system, digital signal processing, no filters. The world will be surrounded by the noise. Why? The Fourier transform is a technique. Right now I am talking. You are listening to my voice. So that is basically a kind of time domain. X-axis is time, Y is the thing. So, but let's say I'm talking in a mic, right? And a generator is working in my back, right? So the generator noise is going to be picked up by the mic. I'm going to talk. So both going to go into the mic for the audio system. So now the thing is how I make sure the person in the other side or the audience does not affected by the generator sound. So the sound that they are interested in my voice, not the generator sound. So I need to filter that noise out, right? How I do that? So there should be a way. I need to know what is the frequency of that generator noise, right? So to understand that, we use the Fourier transform. So Fourier transform is a mathematical model. You can just keep that as a black box over here. Input is a noise, time domain voice signal, or it can be an image, it can be any signal. Output is a frequency histogram, right? So then I identified, okay, my voice is this much frequency, generator voice is over here, then I cancel it out, right? So those are the techniques used in many engineering applications, digital signal processing, analog signal processing, any signal processing without this Fourier transform, we can't do anything. None of the audio programs cannot be conducted because all the people voices will be picked up by the mic. Nobody can eliminate that noise. So luckily we have this transform. Thanks for Fourier to implement that technique to filter out the noise, right? So I will show you this thing in the next tutorial a little bit deeper. Now this is the thing. And Mel frequency septal coefficient. So this is also another way of extracting certain features. We will deep dive into the next lesson sooner and you will learn. Voice activity detection. So that is another technique used in voice recognition. Because I am uploading a video audio clip, I am keeping silent for a while. Then I am saying hello means it only need to pick that hello, that when I start to talk, not that silence part, right? So that is called voice activity detection. And again, let's say there are a lot of musics going on, there is noise in the background, everything, all the sounds are recorded. Then I come and say hello, then it should pick up that hello, not the noises in the background. So that is done by voice activity detection. This is again an ML technique, right? Machine learning technique. So convolution neural networks are there, recurrent neural networks are added to that. So a lot of features, totally 256 values were extracted from my voice, store it into a vector embeddings for the database. So when I talk back, it go through that vector database. Okay, this guy's voice is matching with this guy voice 70%. So he might be this person. Then it say, hey, load me. That's all. Very simple. So for that, we are going to use Resemblizer library. So Siri, Google, many other voice recognition system, they use this kind of libraries. Okay. All right. For first, we will install the library, right? So definitely you should connect to the Crosswalk. Why is that? Crosswalk. Sure. Okay. So connect to the timing, GPU timing, because we are going to work with the CNN based, that means like convolution neural networks based library, Resemblizer. That means we need the GPU to run because we are going to send the whole features as a method. So we need that one. So let's install the Resemblizer library. This is nothing but a library used, which is trained to extract the feature from audio signal, 256 features, and save it in a vector. So that's true. Okay. Let's install that one. It might take a little bit time because it's little, how to say, little heavy one because it's a CNN network. You can understand, right? So we are installing it. So the backend, whoever joined through the online, so please make sure, like, if you have any doubts, let me know. Okay, there are around 5 people or 6 people there, like 4 people with para. Yeah, raise your hand or stop me at any time, then ask me the questions. Okay. So because today's lesson is going to reveal a lot of techniques that used in engineering, right? So we teach these things to MSc, PhD students, plus undergraduate students, whoever gets selected. These are like high-end mathematic techniques for signal processing. So once you install, it will ask you to restart the session. Just click restart because it will take that into consideration. So now the session is restarted. It will come up over here again with the T4. Make sure you have the T4 symbol over here at the corner. Right. So then we are going to install another library called IPython. So this is also important to process our audio signals, right? To work with audio signals and do some stuff. So we will. So now we need to collect certain voices, right? So unlike I added a part, you can record your own voice in face in Google Colab last time for the face recognition. The Google Colab has certain issues in recording your voice. So that's why I didn't add a part to here to record your voice. You can record, but it won't be very good recording. So let's use recorded voices, right? So we have to have some recorded voices. So if you go to the platform again, I have put train data, test data, right? So these are the train data and test data. Download them. Go here and click download folder and go to the test data. Go here, download folder. Download both the stuff. Okay, download both the stuff. Once you download it, you will have a capital letter base train data, right? This one. Similar to that, you will have the test data zip folder. Click and download because we need to download that. I'll give few minutes to download. Download the test data and download the train data. So while you are downloading, I will let me open up. So once you downloaded it, just make sure you extract all. Okay, once you extract all, you will be getting this folder again. Open it up. There again, there is a small zip folder called train. I'm going to extract this also, right? Extract all, right? I'm going to extract all here. Once you extracted, another folder will come. I open here and open here. Once I go, I have 8 voices saved. So the first voice is Biden. You can play and see the Biden voice. 10-second voice clips. Right? Only 10 seconds, not
around. Is that Ruth Ann? And that former Governor Ruth Ann Minner. Most importantly,
10 seconds. Elon Musk, 10 seconds.
I was trying to think, what is the most useful thing that what could I say that could actually be helpful or useful to you in the future? I thought...
Right. So this is enough. 10-second video clip is enough because we are going to extract the features. So that is more than enough. Even your Siri, Google Mini, they just ask you to say, hello Google, hi Siri, good morning, what's the weather condition? That's all they need. So less than 10 seconds they ask, right? To recognize your voice. Linus, I don't know who this person is, but I found this audio, so I just put it over here for testing. Margot is a famous person. Obama, everyone knows. So we have Obama's voice as well.
Tonight, more than 200 years after a former colony won the right to determine its own destiny.
So like that, I got even Taylor Trump.
Very long and very hard over a long period of time.
Trump's voice is
and we owe her a major debt of gratitude for her service to our...
Because many people have mocked Trump during the election using those clips. A lot of funny audio clips are there, Trump. But others, it's very limited. Even Biden, few are there. Obama, I found it hard to find. I found a speech and trimmed it off. So these are the data that we are going to use. Okay. So only 10-second video audio recording that you need to do. It can be in a WAV file format or it can be in an MP3 file format. It doesn't matter. So I have it in the WAV file format, easy for me. So now I go back to this tutorial session. What is this? Okay. I'm going to upload the data. Right. I'm going to go choose files, train data. I'm going to upload this train zip folder. Okay. I'm going to go here. I'm going to go to this extracted train data folder. Under that, there is a train small TRAN, small letters all. That zip folder I'm going to upload. So once you open it up, it's going to upload that zip folder. All the 8 voices are here. All the 8 voices are here. It will take a couple of minutes to upload based on the internet speed as well. Let's upload that one. So what we are going to do? So nothing. We're just going to upload, rename the audio file that you record. It can be MP3 or any format, any audio format, and put it to this library that we have installed. The name is Resemblizer. So the Resemblizer library. Then we are going to extract the features and we are going to save those features in the platform. When we talk back, We are going to compare it. That's all, nothing else. Okay. Same as the face recognition. It's not a big deal at all. Only you need to have this Resemblizer library. So upload this audio to the zip folder to this platform. There is no training needed in this scenario because it's not a deep learning or ML. They are using a library which is trained to extract features. So it's very quick. If a new person comes in, you have to have a security check-in with the voice recognition system. Just ask him to record 5 seconds or 10 seconds clip. That's all needed. Then he's set to go, right? So the same as the face recognition system. But when it's come to security, this is not a good way to go for, because now the deepfake voice synthesis techniques are there. So you can record my voice for maybe 10 seconds or 20 seconds, put it into an AI platform. The AI platform will identify the features from my voice. When you type a new text, it will send through the features again and regenerate the voice. Exactly, it will look like my voice, right? 90% most of the time. Maybe including the tone, right? Including the tone it captures. So deepfake voice thing. So you can see many TikTok videos, people use those stuff. They use Elon Musk's voice to convey many messages. I also believed at the beginning. In the TikTok podcast channel was producing Elon Musk thing, and Elon Musk is talking over there. Certain informations are shared in Elon Musk's voice, right? If you closely notice that video, his lip sync is not at all synchronizing with the audio that coming out from the phone. So that means it's a deep fake video. They are trying to convey whatever the message that they want to convey through a podcast channel using Elon Musk audio. So if Elon Musk is talking, you will believe because he is the guy, crazy guy. He have done certain things which is possible, right? So you will believe automatically. So these marketing people are heavily using those stuff. So now we have uploaded. Once you have uploaded, you can find the train zip folder over here. So yeah. You uploaded? Yeah, cool. Is it uploaded here? Yes. Train. Yeah, it's uploaded. What's the issue? File not found. Let me see. Test data. Now you have uploaded the test data. It's a train. Yeah. You have to upload the train data. First, we'll come to this test data later. So upload the train data again and do the same thing. Okay, so I have uploaded the train zip folder. Then this is in a zip folder, so I need to unzip it to get the files out. So I'm going to unzip. This code is to unzip all the things. So once you unzip it, you can go back over here and see. These are the train. These are the train folders, and all these 8 voices are getting to this platform. So now let's load couple of voices and listen. Maybe the Trump voice. I just loaded the Trump voice over here, right? Then you can listen to that Trump voice over here. There are the libraries to work with these audio. So this is process wave. Wave is the file, and import path, TQDM import. These are libraries when it's come to
very long and very hard over a long period of time.
So you can listen
and
to
we
those
owe
audio
her a major debt of gratitude for her service to our.
So maybe you go copy path, Obama's voice, and place it over here, and play it. Obama's voice will be loaded over. So you can just go to here, copy path, and place it over here. That will play the audio. So like that, we can play all the people.
More than 200 years after a former colony won the right to determine its own destiny.
Right. So like that we can play and check multiple voices, nothing here. So now what we will do is we will unleash the power of Resemblizer and convert audio clips into vector embeddings. That's the next step. First in the face we identify the faces, right? Take the photo of a person. Then the second step, face detection. Then after that, face embeddings. Third step. Here we have an audio signal. Second step, voice activity detection. That means when a person talks, it will get activated, similar to the face detection. Then from that voice activated detection places, we are going to have the embeddings created, right? That's all. So now we have the audio thing. So using the Resemblizer, because in the Resemblizer also look for the voice activity detection. So we don't want to do it separately. Earlier what we have done, we have detected the face and stored the embeddings. In this case, we are not going to do it because this Resemblizer library itself doing it. So we don't want to separately do it, right? So once it comes to this voice activity detection, it's automatically doing it while running the code. Here I am using the wave file, so I have created the wave. If you are going to use an MP3 file for the format, just change it as .mp3, that's all, okay? Since I have all these audio files in wave format, I have used the wave, just play it. So now you can see Elon Musk, Margot, Trump, Taylor, Obama, Ryan, Biden, Linus are extracted. So these are the people voices that we have done. So now what we will do is we will extract these embeddings into this vector store. So now we are going to extract the embeddings using these libraries, okay? So again, when we are working with any machine learning library, as I said, we have to have this NumPy. And LibRosa is another library. I will deep dive into the next lesson, right, that we are going to do today. So now you can see number of wave files processed, 8. So 8 files were processed and the embeddings were retrieved. Let's visualize the embeddings over here, okay? So these are the embeddings, total 8 embeddings stored in a vector store. 1, 2, 3, 4, 5, 6, 7, 8 in the middle, right? So let's see what are the vector store for certain people. By clicking this code, we are going to create a non-embeddings database storage, right? It's going to be a list, empty list, you know, list. Somewhere we have learned in the second week of the Python class, we learned about lists, tuples, dictionaries, kind of thing. So we are going to save these embeddings as a list, right? So I created an empty list and go through these individual embeddings and save it over there with their corresponding name. So let's visualize those saved embeddings. So you can see embedding ID 1. So these are the ones. So these are the embeddings, 256 values. So stored embedding vector. So who is the embedding 1 guy? The embedding 1 guy is going to be Ellen, right? Here, Ellen is the embedding 1 guy. Then the embedding 2 guy is here. You can see the first value for Ellen is 0.0. The first value for, who is the second guy? Margaret, right? Second value, the Margaret is 0.010. Embedding 3, here you can go back and see who is the guy? Trump. So the Trump has a 0.0497. So all the values are different because each person voice has different tone, different pitch, different style, everything. So all together extracted by the vector Resemblizer library, and we have stored as a list in our platform. Okay. So now let's test it. Okay. To test that, what we need to do is we have to upload an unknown audio, right? Unknown audio. So to do that, I'll just go back again to the test data that I have downloaded, right? And extract the test data, right? Extract the test data, and you will find these test audio files over there. You can find another test data and unzip also. I'm going to manually upload these test things over here. Okay, I'm going to drag and drop all these test 1, test 2, test 3 to my platform. Right, once you do it, it will be get uploaded test 1, test 2, test 3. So these are sample test 4. So let's load this guy and see. We will guess whose voice is that. So we will go here and change the path in the top. Right, top we have loaded the voice and we played it. We'll just play it out over here and we will see whose voice is that.
And your mother was begging Barack to stop.
Whose voice is that? What do you think? I'll play again. The test 1.
And your mother was begging Barack to stop.
Kind of Obama. Okay. One guess Obama. Okay, let's see the second audio that I'm going to test. Whose voice is this?
I'm Joe Biden, and I approve this message.
Okay, never mind. Okay, so third one.
And a woman that looks like that has to have her own special scent.
So we can recognize our brain is capable of doing that. Let's test the same thing over here. How these testing based on the vector store works. So I'm going to go copy this path. I'm going to place it over here. Right. I'm going to place it over here. Content 1, test 1, MP3. Right, in the test data. Let's play and see.
And your mother was begging Barack to stop.
So this is Obama's voice, one guess. So these are the vector embedding store that we have generated. And let's test who is it. So this one we need to copy the path again and place it over here. Right? Then we'll play it and see. Hold on. Homer. We don't have a Homer data set over here. Give me a sec. Hold on. So yeah. There is a small issue. We have to copy this. Yesterday I tried with a different data set, right? So that's the reason. Just copy these vector, and we have to add it over here. Right? We have to add it over here. Okay, add it over here. Now play it because it's getting the embedded system 1, 2, 3, 4, 5, 6. Earlier it gave Homer. Homer is the second choice. So here now we will see it. Whose voice is that? Yeah, it's correctly identifies as Obama. Right? Because what we have, vector 1, vector 2, vector 3, ID. So we have to give the name in the order. So now it's identified as Obama. So let's test the second person voice. Who is that? Test go. Copy path. I'm going to go place it over here. Play it. And the second path is Biden. Clearly identified. Test 3. Copy path. And I'm going to put over here thing. And I'm going to play. It should be Trump. Yeah. So the model, nothing else it does. Once you upload an audio clip, it extracts those features using this Resemblizer library and compare with the existing vector list that we have stored over here and go back and identify, okay, if this is the vector matching is actually number 2, then it come back and search who is the number 2 or 3 person, then Trump. Then it prints it as Trump. That's all. Right? The same as face recognition system. So now we have built up a system for voice recognition thing. But this is very simple, right? Within half an hour we have done the tutorial. But this is not the thing that we want to learn, right? As an engineer, AI engineer, one thing is you should know how the libraries work. And also, second thing you should know how the library performs. What are the libraries we can use for this particular work? One thing. How those libraries work in the back end is the second thing. So you were able to do the testing, right, successfully? Have you done it? The testing? Yeah, okay. So it will be most of the time 100% correct, right? So now, when we uploaded these things, then it identifies, right? Clearly. Cool. So now, if there is a voice which is none of them, it will find out the closer thing, then based on the threshold value, we can eliminate that, right? Okay. So now we are going to move into the second lesson. That is little bit going to be hard for certain people in online, even in the physical, but it's not a rocket science. We are going to learn now. Okay, so let's finish this one. This is the voice embedding based voice recognition system. So as a summary, you collect a certain number of voices for a short period of time. Use the Resemblizer library and the NumPy library to extract the vector embeddings, 256 values for the voice, and you save it in a list. So this is your database, right? Once you upload an unknown voice, it go through the list, identify the third number. Okay, this new vector is matching mostly with the vector number 3. Then it comes down and check in the list who is the number 1, 2, 3, Trump. Then he print the name over here as Trump. Simple, right? So how it belongs to machine learning? Because this Resemblizer is a CNN based library, right? It's trained on a CNN based thing. So once it goes through this thing, it will be able to extract all the features, 256 values. Cool. Successfully completed an audio driven speech recognition system, which fairly used in Google Colab, Google Mini, Google Home, and Siri, or whatever the voice features you use. Even in Ben's car, they have this voice active recognition system. So all these things can be done just using this library. It's more accurate. Most of the places it have been used. Right. Now we will leave this part. We will come to the second part of voice recognition based, deep learning based voice recognition. So before I go, I will go and clear all the outputs I generated, because as I said, certain libraries, anyone with a link, okay, done. Okay. So you can go edit and clear all outputs, right? Otherwise, you might see sometimes the output as well. Go to the edit, clear all outputs. So now we are going to go into the deep learning based approach. Even in the face recognition system that we have discussed, I told it can be done deep learning based approach as well. But what I didn't tell you is, because it's straightforward. If you have an image, you detect the face, extract the face part, and it's an image. It has pixels. If it has pixels, definitely you can send it through a matrix CNN based neural network. Then you can get the output. But when it's come to voice, that is not the case. It's not a pixel value. It's a time. You have Excel file, 2-column Excel file. That's all. The first column is going to be time. The second column is going to be your voice magnitude. Time, voice, magnitude. So like this, time, magnitude. It's a kind of a thing. So you cannot use this as an input for the CNN based or deep learning based neural network. So that's the challenge when it's come to voice. Image, no worries. You have a matrix, you can send through the convolution layer, filter, max pool, finally come to the thing. But in the voice, we have only a time and this thing. Any idea how we are going to do it? So that's what we are going to discuss, because deep learning need matrix based stuff. Then only it can perform, right? The feature extraction. Now how we are going to do that? So there is a certain technique which is called as Fourier transform that I have discussed earlier. We are going to go deep dive. So first install all these libraries, right? Okay. Session. So I will cancel the previous session. Right. I don't want that voice encodings. Close. Then play it out. So these are the libraries that we are going to use. Okay. So connect to the T4. because we are going to use the GPU. Why? Because we are going to train the model. This is a deep learning based model. We are going to do the training. So to do the training, we need GPU power. So here if you see, these are the libraries, but what are those stuff? What are these stuff? So these are the PyPlot library formats. So we are going to deal with a lot of graphs underneath in the upcoming columns. So what we are going to use is these kind of plots. So I just defined all these parameters over here. It will simplify my work. I don't want to go and say, okay, this is the plot, this is how you have to plot. This is the plot, this is how, for each and every plot I don't want to define. So I defined it, everything over here. What is the size of the axis? What is the label of the axis? It should be a bold or it should be italic. Everything I have defined in the library itself. So we have uploaded the library. So now the data set that we are going to use is a presidential campaign database. Right? We need to have, unlike the voice embedding based voice recognition, for the deep learning based voice recognition, we need a lot of data. Right? We need a huge amount of data. So at least we need to have maybe 15-20 minutes of audio voice recordings of a person. Minimum. It's not enough. It's not enough at all. But at least maybe 2-3 hours of voice recordings of a person will help to maintain the train. So in that case, we need to have a certain database, right? So I'm going to use this particular database. If you go and click here, which will open up the Kaggle account, right? Which will open up the Kaggle account, which is US election 2020 presidential debates. So day before yesterday, there was a debate happened between Biden and Trump. that debate, Biden talked something at the end, right? And the comparing guy asked, what do you think about, what is your point to Trump? And Trump said, I didn't even understand what he talked. I don't even think he understood what he talked. Biden is lost, completely lost on his mind, and I don't think he's going to make it to this election. But there is a scenario Biden might come because of that court case issue of Trump, right? So, but Biden have a very good brain team behind him, so who will work on the marketing. We'll see. It's going to be very interesting and funny. Trump and Biden, right? So this is 2020 elections. During this time, I was in US, right? So these kind of debates and everything, I was waiting and listening everything. So these are multiple debates happened. So this is a good system, right? So they identify potential higher potential two candidates who can be a president, come in front of a public, ask question, they debate. So if we do it for Sri Lankan, we will identify who is a real person. But nobody have the guts to do that in Sri Lanka. Nobody will do it. And people, we don't care. What we need is free stuff for 5 years. If they don't give what we want, next 5 years, another person. So no policy, nothing. That's why we are struggling in this country like this. So now the thing is, these voice clips are there. So I'm going to take only one voice debate, so which is 1.5 hour long. In that 1.5 hour long clip, we have the comparer's voice, Biden voice, and Trump voice, right? So now the good thing in this database, they have went through this database MP3 file and they have sectioned, okay, this is the comparer's voice part. This is Biden voice part. This is Trump's. They have sectioned those voices. So, and they have put it over here in this Excel file. Chris Wallace 120 and 211. Chris Wallace again, and these 2 seconds, how are you doing, man? Vice President Joe, all these things are extracted now. So this CSV file has all these extracted types. So we are good to go. What we need voice clips of certain people. Now I have 1.5 hours of total length of audio clip. So these people also tell which time which person speak. That's all I need. So I have a lot of data from that data file. So that's what I'm going to use for this thing. So the Chris Wallace is the moderator, President Donald J. Trump and ex-Vice President Joe Biden. So that is the thing. So now we are going to come and use this data set. So don't download anything because we are going to download directly from the Kaggle. Last week you have a Kaggle JSON that you have downloaded in your platform, right? We are going to use that. I don't know what Google is not trusting me here. Okay, we'll see. Okay. So now we are going to use, so go to the Kaggle, your last downloads option, you can find a Kaggle. Right, I just put it over here. You can find the Kaggle.json. That is going to be your JSON file to connect to your Kaggle platform. If you do not have that Kaggle thing, go here, click here, and go to sign in page, right, and register, and you can go to the home and go down and find the API key and download, right? Or else for easy access, I will upload my, no, you can download. You already have, I believe, right? The Kaggle, did you have it? Okay, so can you go and register? Oh, sign in. Right, I'll sign in using my location. Sorry. For the last week, we have done that. So I'll just go here, Kaggle. Okay, okay, fine. And I'll just go there. It's a unique ID for you, basically. So then I sign in with Google. Then I go here and I go to the settings here, right? This is me. Go to settings and go down and you can find an API key. So download it first if you do not have from last week. So that is API. So I'll just create a new token. I'll download that now. Continue. Okay, I downloaded now, right? Just create an account, go to your profile, go to settings, come down to API and create a new token, and the token will be downloaded as Kaggle.json. Once it's done, let me know. Because this is what we are going to use. You don't want to download the whole data, you can just directly map from the Kaggle itself. Okay, downloaded. Let me know. You have done it, right? Have you done it? No, you don't want to download. So you create an account, go to here to your account, go to settings and go to this API, right? Go to the API and click create new token. That's all. Then it will get downloaded JSON file. So we will directly download it from the Keras Kaggle to the Google platform. If you have this JSON file, that's all you need. You got it? You also got it? You got it? Shall I? Okay. So here. So there is a link. You can create and download. Okay. Go down. What happened? Somewhere it got deleted. Yeah. So it's fine. Yeah. Yeah. Okay. So once you download it, keep that over there. We are going to use that data file. Okay, cool. We'll go back to this system again. Our tutorial back. And yeah, this is our tutorial. Okay. Right. Keep that Kaggle file. We are going to use that. So now the thing is, somewhere it got detected. How come? Hold on. Hold on. I'm just going to share option to mentor. Okay. Yes. Okay. So after downloading that thing, we are going to use the understanding the MEL spectrogram. So where is that? Okay. MEL spectrogram is, so that is the important feature that we are going to learn. Basically, the thing is, so as I said, we need a kind of a two-dimensional matrix as an input to the CNN. So what we have is this signal, amplitude and the time. If you record the voice and play it out, this is what you will get. So this cannot be an input because it's just time and amplitude. As a matrix, you cannot give it up to the CNN, right? So there should be a way to convert this into a kind of an image which has pixels. Then you can put that into the CNN layer. Then you know what to do. Rest of the thing for the feature engineer. So how we are going to do that? So to do that, we need to convert this time domain signal into a frequency domain signal. Okay. For example, if this is the time domain signal with multiple sinusoidal and everything, if you send it through a Fourier transform, that is a mathematical model. You just don't want to think about anything. Input is a time domain signal, output is a frequency domain signal. So it will identify those frequencies in that signal, right? So that is the thing. Input is a time domain. If you put this input into it, it will be able to identify all the frequencies. For example, this is an audio clip of a music program. Imagine. Then there a person is singing, drum is playing, guitar is playing, violin is playing, flute is playing. Everything is in a different scale. It's different pitches. So how you identify? Okay, now I need to, I have only one mic, right? I'm recording the whole system through one mic, guitar, audio, everything. So everyone is playing, I'm recording through one mic. So I found out the flute sound is not sufficient in the output. So how I can amplify the flute? Because all the things are going to come through one mic. So in that case, I need to identify where that flute frequency is located. Then I go and identify that frequency. Then digitally, I can amplify that frequency signal, right? Then in the output, you will hear a loud fluting. Now not it's happening. Each and every equipment have a separate mic. But in case if you have one mic, you have to have a condition. You can do that as well. Okay. So now this is a musical signal. Let's say we are going to send through a FFT, Fourier transform. First, you will see this. I have used FFT. FFT is a technique which can convert the Fourier transform in a faster manner, right? You can keep that in that way now because this is used for digital signal. We don't want to go deep dive into too much of mathematics. But what it does is the FFT is a way of computing the Fourier transform in a very high speed manner. Okay. Keep that in mind, right, for the digital signal. So once you convert this signal into a frequency domain signal, here you can see, here the amplitude is there, here the time in seconds, right? 1000 seconds, 10,000 seconds, 20,000 seconds, 30,000, 40,000 seconds, or milliseconds, right? I don't know what is the unit. When you convert that, this is the spectrum that you are going to get. This is the frequency spectrum. So now this is the speed signal. Once you convert, send it through a black box which is having a mathematical model to convert this time domain signal into the frequency domain signal, you will get this one. In the x-axis, this is a frequency. In hertz, the magnitude of those frequencies will come. So there is a frequency in 200 hertz, 400 hertz, 600 hertz, 800 hertz, right? So that is there, but in a signal that is not directly there. So it correlated, but it's not directly correlated. F is equal to 1 over t. That is for the sine signal. That is for the sinusoidal signal. Frequency is divided by 1 divided by t. That's a period and everything. So I'm not talking a sinusoidal signal. My signal is totally random. So in that case, it's not correlated directly, right? Sinusoidal or periodic signals. But when it's come to voice signals, you have to do the Fourier transform to convert it into a scale. So there is a correlation. That's why the mathematics model can do that. Otherwise, it cannot do it. There is a relationship. So when you send this voice signal through the Fourier transform black box, it will be able to create the frequency spectrum. So you don't want to worry too much. Just imagine like a black box. So I teach digital signal processing in campus. I teach 2 weeks to explain this Fourier transform to discrete Fourier transform to fast Fourier transform. It's a big lesson. Okay. So now we assume, okay, we know there is a technique called fast Fourier transform. When you send the time domain signal, it gives you the frequency spectrum of that signal, right? So now you have the frequency. Let's say this is the noise part. I just want to eliminate. 400 is the generate, hertz is the generator noise coming from my back. What I do, I just go and filter out that part. So that's how the digital filter, analog filters are coming in, right? So we should know what is the frequency over there. So to do that, we use the fast Fourier transform. So as I said, we are going to use the data set, and this is the data set. And what is the spectrogram? Because the initial heading is MEL spectrogram, right? What we have learned, we have the time domain signal, that is a voice signal. From that signal, I will be able to convert that into a frequency domain spectrum. Then what is the MEL spectrogram? So now we have the input time domain, and we have a windowing method. I told you, we analyze by window, right? Window by window. So this is the window length. Then I'm going to move this window section by section, right? And I'm going to capture this voice. And I'm going to capture this voice for this window area, and I'm going to convert that into a window segment. But if you see, this window and this window are overlapping in this area, right? In this area, it's overlapping. So I do the fast Fourier transform analysis to get the output 1 and output 2 and a combined overlapping avoided output FFT3, because I can get these are overlapping window. I get the conversion into a frequency domain, output to conversion into frequency domain. If you see this certain part and this certain part is same for me over here and here, and finally I eliminate that part, subtract one from each other, and I get the FFT3 output, that is separate window length, which is going to cover here and cover here. So this is how we use the window methods to extract the feature even in the embedding, previous thing in that library. That's how they do in the background. So now the spectrogram looks like this. See this? So you can think of a spectrogram as a bunch of fast Fourier transform of stacked on top of each other. It's a way of visually represent a signal's loudness or amplitude as it varies over time at different frequencies. So this is a one way to represent, and this is another way to represent. So what we do, in the voice signal, we move the window, and each window we rectify the frequencies, right? Fourier transform. And we map it to this thing, right? So the y-axis is converted into a log scale in hertz. You can see this is the hertz and this is the time. So what we had earlier, time versus amplitude. In the second, frequency versus amplitude. Now this is frequency versus time, right? And the magnitude is shown in color scale. Is it looks like an image now? Is it looks like an image now? Yeah. Then can you use a CNN on this? Yes, right? So basically you have the frequency, you have the time, and the magnitude is shown in the color scale. So it's kind of a image right now. So now this can be used as an image for the feature extraction for the CNN. Clear? Right? So earlier the problem for us, how we are going to convert this time domain signal into an image type of signal, right? Now we have done it. That is called spectrogram, right? This is a very important thing. Speech to text, speech synthesis, everything that we are going to work over here is going to rely on this spectrogram. You clear, right? Somewhat. No, I'm not using mathematical equation. Right? If you want to do this, it will take a long time to solve this equation, right? Integration equation. So just imagine as a black box where you put the time domain signal, your audio speech signal, output is a frequency domain signal, right? That is fast Fourier transform. You put this one in the black box, you have a window, which window is going to move and take the features. And that is the window moving time. Time is the x-axis, this is the window period, right? This is the window period. And in that window period, these are the frequencies in that window period. In that window period, that frequency magnitudes are in the color form. How smart it works, right? So the engineers solved the problem. They have seen it, but they don't have an image. Created an image using this technique. Image type of a material. It's not an image. You can break it into numbers now, right? As a pixel number, we have the numbers, right? That's all we need for here. So what is the MEL scale? Because this is spectrogram, not MEL spectrogram. MEL spectrogram is based on the MEL scale. So studies have shown that the humans do not perceive frequencies on a linear scale. We are better at detecting difference in lower frequencies than higher frequencies over here, right? So for example, we can easily tell the difference between 500 and 1000 hertz, but we will hardly be able to tell the difference between 10,000 and 10,500, right? Because it's our ability, even though the distance between the two pairs are the same. 500, 1000, 500 different. 10,000, 10,500, 500 different. But we cannot say that difference, but we can say 500 and 1000 different. It's our human hearing ability. So based on this ability, MEL came up with someone called 1937, Stevenson, Walkman, and Newman proposed a unit of pitch, such as equal distances in pitch sounded equally distant to the listener. So this called MEL scale. MEL scale. So the magnitude is little bit differently mapped into the MEL spectrogram. You can see this is the spectrogram. If you send this through this mathematical function, because of the human ability, you will be able to convert that into this MEL spectrogram. It's a spectrogram. Go through this MEL scale and you get this MEL spectrogram. Clearly see here, this is kind of purple and this area are dark. This is spectrogram. Here it's very light purple compared to the previous one. Here it's very bright. Here it's little darker. You can see the difference, right? And here in the middle, it's very brighter. Here it's not brighter like that. So there are differences. So the MEL spectrogram means, considering the human ability on hearing, we have constructed the spectrogram, right? So now we are ready to train a deep neural network. Clear? Any doubts? Is it hard to digest? I know sometimes it might be, but only thing that you need to know, I can skip that and I just can go without telling you, just use the resemblizer and that thing. But we have to know what the resemblizer library does. And we need to know the spectrogram techniques, because this is the one that we are going to use for upcoming lectures. For example, we need to know this one in order to deepfake the technology voice. Without this, you can't do that. You can use a library that is there, but you should know what is there in the backend. If you don't understand, just go through this text. It's very simply made for you to understand, right? You can read and understand, or else simply again summary. You have this voice signal and you go through a window, time window, a particular time window, extract that frequency time domain signal, send it to this frequency transform black box, convert it into a frequency signal, and put that frequency signal through the spectrogram, where the frequency is the y-axis, time window is the x-axis, and the magnitudes are in color. Now you have an image. Then, due to the human ability on hearing, these people came up with some mathematical function. You send through the mathematical curve, you get that MEL spectrogram, which enhance the certain magnitude based on the human hearing ability. Right? Now we are going to use this image to train the CNN. So now that's all. In a summary, we took samples of air pressure over time to digitally represent an audio signal. What you hear is an air pressure, vibrates, come to your eardrum. We map the audio signal from the time domain to frequency domain using the fast Fourier transform, and we performed on these overlapping window segments on audio signal, right? We converted the y-axis to log scale on the color dimension amplitude to decibel to form a spectrogram. We mapped the y-axis frequency onto the MEL scale to form the MEL spectrogram. So here the frequency you can see 496, here you can see 8192. So certain frequency part is cut off over here. So it's MEL spectrogram stop. Is that clear? At least 10% clear. Okay, that's enough. That's enough. Don't worry, right? If you do not understand, no worries at all. At least something you know how this is working in the back, because it's a very big engineering stuff. We teach this thing in one semester, digital signal processing, right? And the fast Fourier transform, it's a 4 lecture class, right? So you can't understand it in one thing, but the concept you can understand. Time to frequency domain shifting, that's all, right? So, and you can do how to convert the spectrogram. All good now. So now we are going to download the data, because we need a lot of data, because we are going to work with this thing. Go to the downloads, drag and drop the Kaggle file over here. Okay, right? This is the Kaggle JSON. Then first we need to install the Kaggle. We have done the same thing during the last lecture as well. I'm going to, first you have to upload that Kaggle JSON file to this place, right? Then you install the Kaggle. We have done it similarly for the same way for the emotion recognition system, and connect to the library Kaggle, and finally download the data. Once the data is downloaded, you can go and find it over here. US election 2020 presidential debate. It is a zip folder, right? It is a zip folder. So what we need to do, we need to unzip it. So let's run this code to unzip. So all these code, we have done the same thing for emotion recognition last week. So I don't want to go through it again. So the question that I asked during the last lecture, how you can perform a CNN in a voice signal? And now the answer is, we are going to convert that voice signal into an image kind of a MEL spectrogram, and this is going to be the input for the CNN layer, right? Cool, right? Okay, now let's, we have unzipped it already. Let's listen to the audio, right? If you unlock this one, there are multiple things. So this is the first presidential debate CSV. This is the CSV file have who spoke during which time period. right? And this is the second presidential debate CSV. Then this is the second debate presidential database text file. And this is the MP3 file. So we have MP3 file, text file, and the CSV file. So we are going to work with the MP3 file and the CSV file. So let's load the first debate presidential file over here and play it and listen how it sounds like. So I'm just loading. It's 1.5 hour audio. It might not play sometime. The reason it's too heavy. 1.5 hour, right? 1.5 hour. So we will let's leave it. No, let's go and see. We will try the another code that we have tried. Go here, and we have the voice recognition embedding. Let me go there and download that one. Copy that, paste, and leave it here. We have listened to something here. Let's listen in this manner. Okay, let's see if this works there. So I'm going to let me add this one and see whether it works here or not. Now, the reason behind this is 1.5 hour long. So that's why it's not loading into the platform. It doesn't matter. So this is the same code, but it's 1.5 hours long. So let's listen to this presidential election audio. We should listen. Otherwise, there is no point. So I'm going to download it. Right? I'm going to download this one and we will listen. Let's it download. Until then, we will perform the operation. Okay. So now we have an audio frequency which have 3 voices: compare voice, Biden voice, and Trump voice. And we have a CSV file which mention the timeline of the speaker's speech. Okay. Now let's create the MEL spectrogram for that whole 1.5 hour audio. Right? Let's run it. It's going to take a little bit of time. Right? Because it's need to compute first what is happening. 1.5 hour audio is loaded into the platform, and we are sending these windows over that voice, taking that voice and doing integration and find out the Fourier transform for each signal, right? Convert that Fourier transform frequency and the time domain into a spectrogram. Send that spectrogram through the MEL curve to create the MEL spectrogram. So this is a huge mathematical operation. It took a little bit long time for us. Now this is the MEL spectrogram for our audio signal. Did you see? The time 1 hour and 30 minutes and the frequency goes up to 8192. The color scale is there. So now we have constructed the MEL spectrogram. So don't worry how I have done it, because I have loaded all these libraries over here earlier. This one, Librosa, right? Display. So this is the one that we use for MEL spectrogram. NumPy is there to do that. Librosa is a library. We have to plot this one. For example, I will show you here. So here, Librosa feature MEL spectrogram, right? So I imported the library over there. So I'm using that over here. Then I just plotted the spectrogram. This is cool now, right? Let me see whether I downloaded it or not. Yes, I downloaded it. Let's go and have a look at that. Okay, let's play it. It's an MP3 file.
Good evening from the Health Education campus of Case Western Reserve University and the Cleveland Clinic. I'm Chris Wallace of Fox News, and I welcome you to the first of the 2020 presidential debates between President Donald J. Trump and former Vice President Joe Biden.
20 million people getting health care. Because you weren't president. Because you weren't president screwing things up.
You were.
So here's the,
So this is the data that we are going to use now, right? It has a combination of Trump, Biden, and the comparing. Luckily, we have the time limits, so we can extract those audio clips. Let's do that. Okay. So let's plot the energy distribution of that 1.5 hour audio. So it's going to be kind of energy of the signal with time, right? So the audio signal is a vibration, right? Vibration has energy. So what we have done, we converted that energy into a decibel and we have plotted it. So this is how the energy spectrum of the average energy over the time is plotted over here. So this is just for visualization, nothing we are going to use for the machine learning purpose. Okay, cool. So let's visualize these things in certain other ways. So Bell spectrogram is one thing, that's done. But when it comes to audio processing, there are a lot of ways that you can visualize an audio signal. So first, let's load the data file. As I told you, the data file has, let's download it, the data file also. And we'll be able to see it clearly, right? I'll go back, open the CS file. CS. Say you can find, okay, Chris Wallace, right? 120. Oh, this time domain, 829. Open discussion. All these things, the time they spoke is mentioned over here, what they spoke. So this is the library that we are going to talk. Only we are interested in the time thing, 837 and 1840, he's saying something. So we know from 1837 to 1839, President Donald Trump is talking, right? 1814 to 1932, Chris Wallace is speaking. 1933 to 29, Joe Biden. Again, this also Joe Biden. Like that. So it's breaking. So we know the timeline. So that is good. We have the CSV file. Let's go back. Cool. So now I have loaded the CSV file over here. Then what I'm going to do is I'm going to plot the CSV file. Right? So I'm going to convert to second because now it's in minutes. Right? 120, 330, all these things. So by running this thing, I go to the time string, go each and every time in minutes, and I'm converted to seconds. Then I'm checking the minute list and plotting the second list and data. So don't worry too much. These are data pre-processing. So now good evening from Health Education Campus. So this is 80 seconds. Earlier 120 minutes, right? I converted into seconds. And 210 minutes, he is talking this one. Next 210 minutes, 130 seconds I have talked. So now I converted this audio into seconds. Cool? Right. Because I'm going to process in seconds the data. Then these are data certain processing. Okay. So let's play this one. Okay. We don't want to know now what is happening. Just I will explain the output on it, right? These code basically go through the name Chris Wallace, Vice President, President Donald J. Trump, Vice President Joe Biden, all these things again and again. And what it have done is it combined the thing. So what happened earlier, Chris Wallace, it labeled as different numbers, 0, 1, 2, 3, 4, each numbers. Here we combine 0 to 3 and the duration over here, right? We have combined all these things and we will see how the thing works. So for example, if you come here, the first set of speech for 80 and the speaker for 100 and thing like that. So these are pre-processing techniques. We do not want to deep dive into this thing. So we are getting the maximum times that they have spoke and we have put over here, right? So this is the maximum time in the whole data set that they have spoke. And now we will convert this into a MEL spectrogram. Already we have done it, and we'll do it again. So these are the MEL spectrogram values. See, right? It's a sample audio tail that we are loading. This is not up to 19. It will go until certain values, right? So now we have converted the frequency, thing, and the magnitude of here. You get it, right? This is time in seconds, right? That is the x-axis. This is the y-axis frequency, and these are the magnitude in dB. So this is what we got over here. This is what we got over here as an image. So these are the MEL spectrogram numbers, because we cannot send the MEL spectrogram image. We have to convert it into a number. So these are the number which is similar to the pixel numbers. Am I right? Yeah. So that's what we want. So we have done. After that, we are going to do some post-processing to visualize the data. So we are going to use a PCA library. Just I'm going to run it. Don't worry too much. The concept you want to know is the MEL spectrogram is the input, and we are going to construct. So these are different ways of visualizing the certain libraries. Let me show. So we are going to extract first who talk what. So that's what I said. This is advanced. We teach a little bit for MSc students, this one. So this might be little too hard for you, but I'm running the same tutorial that we run for the MSc students. So, but knowing is good. So these are the spectrogram here. So which transform the data using scatter plot, where x-axis the PCA data and y-axis the PCA data. One represent the first, second principal components respectively. So each point is colored according to its index in PCA data. PCA is a library, right? We take 4 components over there. So we use that to process these things. So here, the first component and the second component, it's a mathematical operation. Based on that, we like plot this one. This is a way of visualizing. Nothing, this is not going to be the input to that thing, right? We are not going to do anything with this one. This is just to visualize the audio data. So don't worry. But if you do this one, right, we can get this data and we can segment the audio speakers. So now the issue is we have 1.5 hours data, and we know 80 seconds this guy's speech, 90 seconds this guy's speech, next 90 seconds this Biden speech, next 120 seconds this guy speak. We know that thing, right? So now we need to break those into windows, and we have to create the features. So now that is happening here, right? That is happening here. It goes through the whole audio, break it into pieces, the time that shown in the thing, and creating the speaker segmentation, because we don't want the whole 1.5 hours. We need the data, audio clips of individual people, right? So that is the data that we are going to use. So for that, it goes through the audio file, segment the audios based on the speaker. So that is happening right now, because it's 1.5 hours. We have 80 seconds, 120 seconds, 80 seconds, 90 seconds, like that. It's breaking it out. Okay. Let it run. Okay, done. So now let's look at the data. So now it's created like this. This is the time, that spectrum, the spectrogram for a particular time period, right? And the speaker is Chris Wallace. So if you look at the data, this is the spectrogram for Chris Wallace, and this is the spectrogram for Biden. This is the spectrogram for this guy. Like that, time wise, it just created. So now plot this one and see in the real way how it's going to look like. So this is little advanced, never worry, just know the techniques. We already know how to do the voice attendance system or voice based recognition system using embedding, but this is a CNN based approach, because this is important, this feature for the next lectures also. So if I cover it over here, the next lectures I can just next upcoming lectures will be easy for me. So now we are plotting the PCA data plot, which is extracted by the speaker. Okay, so I'll show you. It'll show clearly who are the speakers and which time they are speaking on. Take a while because it need to process. You know what happened? Going through the thing, come through the frequency, all these mathematical operations need to perform to do this stuff. And this is not the spectrogram plot. This is going to show the time domain, feature extracted thing. Basically, we are plotting this extracted this thing. It'll take a while. So this is one way. You take a low audio signal and you segment it into pieces based on the speakers and you do it. Or else another way also there. You individually upload the speaker. Okay, this is drum for 1.5 hours and you break it into pieces. Then you take drums audio. And as we have done for the decoding small clips, you can upload maybe 1,000 clips of Trump, 1,000 clip of Biden, 1,000 clip of the compare. Then you can do the training separately as well. Right now, what we are doing from one audio clip, we are segment and collecting the data and taking the data and get it into the CNN model. So that's the thing. So that's why it take a little bit of time to segment and do these pre-processing feature engineering. You can do it in the other way also. Manually collect the data and do that. Okay. Oh my God, it's taking a long time. It will take this time. We'll see. It'll come up. So this is important. I cannot skip this one because I show you. Did it run for you? Still running, right? Hope the internet is there. We'll see. We'll see. Yeah, here we go. So here you can see the seaborne axis grid. So here you can see these dots that we have created earlier. Never mind about these three. This layer. See here, there is a purple color one, orange color one, and a yellow color one. Right? Right? We will get this one and we will see it little closer. Okay. I will get this part and plot it little closer and I will explain that thing. So these are the spectrums. So the thing, whoever speak, how many people. So see the yellow, orange, and purple, right? So these are the colors. Let me do that. Let's plot this one. I'll take this part and plot it and I will explain. So speaker Chris Wallace, Vice President Joe Biden, and President Donald J. Trump. So these are the speakers. So let it plot this one. Okay, now you can clearly see this is the 1.5 hours audio clip, right? So I extracted this one and plotting it over here. So now if you see, the purple color one is Chris Wallace, Vice President is pink, and yellow is, or purple, yellow is President Donald Trump. So this is where they have speak. First, this guy talk for a while, Wallace, then purple Biden talk, then Donald Trump, then Biden, then Donald Trump. So no, Donald Trump, Biden, then there is a Wallace in the middle, and Wallace in the middle, then again Wallace in the middle. Like that, the whole clip is breaking into pieces, right? So these are the individual segments that we are going to extract for the training, right? There is not much. If you see, there is a small voice clips, 80 seconds clip, 10 seconds clip, 240-second clip of Biden. But that are the input that we are going to take. So that's why this feature engineering takes too much of time. How we can eliminate these old top faces? By uploading separate clips of a person, right? You record Donald Trump audio for 1 hour, break it into 10 seconds, say Donald Trump, name it as Donald Trump, right? Collect 1 or 2 hour audio clip of Biden, break it into 10 second clip, name it as Biden, right? Different clips, not in a one audio, because matters is when it's come to CNN, it's going to automatically extract the feature, right? So in that case, there is an issue. Biden speaking in a meeting in front of audience. So the clapping sound, whistle sound, everything is going to come. Biden talking in a very peaceful environment. So that is a different way. So you have to collect data based on different aspects, right? Because we don't know in the testing environment, it can be a place where multiple people are there. So in the testing environment, it can be a place where there is no people quiet. So the model should be able to identify whose voice is what, right? So you have to collect those data in multiple scale. So now this pre-processing step is all required. Why? Because we are extracting those voice clips and using that voice clip for the train. But not necessarily this is not needed. Okay. So now we will have this Chris Wallace, Vice President Joe Biden, President Donald Trump, and everything in the name. And we put the name into the CNN layer. No. We have to give a label to these people, right? So let's give it. So by doing that, you will be able to encode the speaker data and plot the same plot with given a number over here, right? Let's write it plot. So it's the same thing, but the Chris Wallace, Vice President Joe Biden, and Donald Trump is given a number because AI works with the number. Last time also for the face recognition emotion, we gave an emotion 0. So you can see speaker 0, 1, 2, right? We have changed the name into a number label. So because what we are going to do, we are going to construct a CNN layer, right? CNN layer, which have, this is the spectrogram image of individual people. We are going to plot with the time, frequency, and the magnitude, right? This is going to be the input for the CNN. So this is for Biden and Trump and the Chris Wallace, 3 people. So this is what we have done. We have an audio signal here. We have an audio signal here, and we have break it down to the pieces where they have talked. How we know? That we know from the CSV file. And these data are plot as a spectrogram. Then this is Chris Wallace, right? The Chris Wallace name goes as 0. So this is the spectrogram going to go into this model. So this spectrogram go into this model, and this is the CNN layer. That means convolutional neural network, which is going to have multiple convolution layer, max pooling layer, and finally coming to fully connected layer and something. Finally, 0, 1, 2. So these are the labels. So when real time, when you plot this guy, right, put this guy inside the spectrogram or the voice clip, it's going to do the same thing, plot the spectrogram for a particular time section, send it to this thing. This guy will send feature extract, finally come. And who is going to have the highest probability? 1, then it will go and say 1 is Biden or 1 is Trump, right? So that's the thing. So they have same thing. For the emotion recognition, what we have done is we have labeled 0 as angry, 2 as something, so the same thing. The name 0, 1, 2, we have labeled it, right? Even in the encoder, we have done it. Encoder 1, encoder 2 in the previous thing. Then it look in the list and we get it, right? Now, speech index mapping dictionary. So what we are doing is we are mapping this 0 to Chris Wallace, 2 to Vice President, and 1 to Donald J. Trump, right? That is done. So after that, we have to do the machine learning code. So what we need when it comes to CNN machine learning, we created the data, we splitted the data, we gathered the data, right? This whole thing is unnecessary if you have individual clips, right? You don't want to care. If you have individual 10-second or 5-second clips, this whole part up to now what we have done is unnecessary, right? So I don't have time to create that many clips for the training. I dragged and did it over here, right? In real time also, this will be helpful for you to do the featuring, right? So that upper part is totally little advanced, and what is happening in the back end is advanced. We teach for MSc, right? So no worries if you do not understand. If you understand there is something look like an image, which is called spectrogram, MEL spectrogram. That is the input for the layer. That is enough for this class, okay? Cool. So now we are coming to the machine learning part. So we have the data, we can create the MEL spectrogram. That is going to be the input numbers that we are having. And now we need to create the training data set, testing data set, normalization, creating the neural network, training the neural network. These are the pending. So I'm going to create the time X series data. I'm going to split it, test size 0.2. Randomly, I'm splitting the whole data into train, test, data. That we have done earlier also. Test and train splitting. After that, I am changing that data into NP array, right? That means array of numbers. Then reshaping. What is this reshaping? That means normalizing the magnitudes, right? I am normalizing the magnitude and doing all these operations, giving an ID and by train IDX. Finally, all these things we have done it for the emotion recognition as well. This splitting the data, normalizing and giving a label for everything, that is done for the emotion as well. I do it. Now we are creating a convolution layer. So in the convolution layer, I'm going to have one convolution layer where is a filter size, which is 3 is going to go through that, and convolution layer 2, convolution layer 3, and output layer going to have softmax, and that is the full thing, right? I constructed the CNN network, right? So this is the way that we have constructed for the emotion recognition as well. So I don't want to go through that again. So now we will train the model. Just I'm going to run it for 10 epochs. So keep that in mind. The data that we have used here, it's not enough, right? And 10 epochs is not at all enough, right? So let's run this for the practice, and the batch size is 50. So I have broken into very, very small pieces, because if I want more data, what I need is I can break the sound clip into 50. So totally 3,146. That is a batch, right? 3,146 into one batch. How many batches? 50. So I have broken this whole audio clips into 157,300 clips. So that means very, 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 very tiny pieces, right? Then I can collect a lot of data for a person, right? If I can enhance the time gap, then the number of samples that I'm going to use is going to get less, right? So this sample is okay, but the size of the sample is not enough, the duration. So if you increase the duration a little bit, then the training is also going to take more time. So to avoid that, we have break into tiny, tiny pieces. The total number sample for the training I'm using is 157,300. So very, very 1 second, 2 second, or nanosecond, millisecond. Now the created CNN network is training. So this is the convolution neural network. After collecting the data, we have created the convolution neural network. Then we are getting it max pooling layer here. an output layer having the softmax, which is going to have 3 layers, and return Keras model this thing. The same way that, that we have done. So I'm running 10 number of epochs to finish this in class. So right now we are having the training going on. 7th epoch is going on. See, the accuracy is very less, 0.4790, but it's keep on increasing. If you go for more epochs, it will definitely reach more than 60, but I don't think more than 60 is possible. The reason is number of sample is not enough. Sample is good, but the sample size is not enough. So you can upload the number 2 thing also. Now I have uploaded only one election campaign. We have number 1, 2, 3 up to all the campaigns in 2020. Then combining them as one audio file and doing that will be more accurate. So you can try that in home, right? Multiple audio clips and save it and combine that, this file, this Excel file. What is that? Here we go. This one, right? This one, see? Time 0.00 seconds. Then the next clip I cut it at 0.02 seconds. That means how small it is, right? And the next step for Chris Wallace is 0.04 seconds, 0.069 seconds. So that means it's in millisecond range. I cut the audio clip in millisecond. Otherwise, 157,900 sample is not possible. That means even like that, some sample are going to go in. It's not effective. If a guy call you and say, can you identify who is? No, right? It's not. But AI will be able to up to a certain limit because it extracts all the features, but our brain cannot. So these are the sample sizes. Like this is 0 to this is one sample. This is the next sample. It's 0.02 is the size, millisecond size, right? So that's not enough. So that's why we are getting, but you can increase the sizes as well. So now the training is done. Let's test the accuracy on the test sample set. So here we have around, test accuracy is around 0.501. Not bad, but still it can be improved a little bit by increasing the epochs numbers, right? You can play it in home and test it out. So now let's see certain things, okay? These are some way of testing. So we will see the encodic 0. 0 is Chris Wallace. That's the guy's name that we have given, right? If you put 1, that is a different guy. So we are going to test on his voice only, and we are going to see how many things get detected correctly. It's Chris Wallace, Donald J. Trump, and President Joe Biden. So we have all these stuff mentioned over here. So let's plot the, what is that called? Confusion matrix, right? So we are processing this data for the confusion matrix. So these are the whole data. It's got detected. So the first time segment from here to here, this time Chris Wallace this much percentage and Trump this much percentage, and it's actually in the percentage. So in the Excel file, the test results is shown over here. Okay, the first segment of this one is Chris Wallace 0.99% detected, Trump this much detected, and Joe Biden. So the final result is Chris Wallace. In this clip, 3,000 and 31,493 clip, third clip. This is the time duration in seconds. The Chris Wallace AI model detected that clip as Chris Wallace 0.32, Donald J. Trump 0.48, and Joe Biden 0.190. Finally, the output is Donald J. Trump. So that's how it tested in all the clips. Is that clear? Clear? Right? So this is the audio clip, time duration. These are the percentage that the AI got detected, and this is the final results. Right? So for example, if you see this clip, 14,676 clip. So like this is the thing, 500, and this is the timeline, time limit. And Chris Wallace, AI detected as Chris Wallace 0.3%, Donald Trump as 0.51%, and Biden as 0.18%. So the output should be definitely Donald Trump because he has the highest percentage, right? Epochs, training, weights matters, right? Because even in the last time, I got a higher accuracy, somebody got a lower accuracy because the weights are random, we are starting. So in the training, yeah, that's a really good question. Let's go here, go to your place. So my first training, my categorical accuracy is 0.4048. How much you want? In the training, under the training. Yeah, see the difference? Because your weight initialization is completely different from my training. From his training, her training, we are going to get different results. So only thing, we are trying to optimize the error, right? So the error is going down here. My loss is here, 1.0574. It's going down each step by step, and my accuracy is increasing each step by step, right? What is your final accuracy? 10th accuracy. My one is 0.4901. Your one? 68. See, so that's difference. It completely depends on the weight initialization, right? It's the training. It's going on. Yeah, random. We can fix it, but it's not a good approach. If you fix it, it will lose the freedom of learning because you are fixing it and saying, like, it's like telling the kid you should learn this. Then the kid is not going to learn in an effective manner, right? So we randomly do it. Okay, we start somewhere. Our goal is to get the optimum value. So we do the training. The mathematical function, you try to optimize the error, come to the highest accuracy. That's all, right? So we never fix a weight, right? It's not a good practice. You can, but it's not a good practice for AI training, right? Therefore, there is another issue. Now, if you see 0.4048, 4200, 4295, 4459, 4505, all the accuracy is increasing. The loss is reducing. The loss is reducing, right? But in not all the cases, this will happen. Because it's a mathematical function, right? So the model will come like this, right? The loss is coming down, coming down, coming down. At a point, the weight comes down, it's going on a good direction. There are millions of weights or parameters are here. And certain change of weights actually increases the loss, right? Then it will randomly change in a different manner. Sometimes it might come down. Sometimes it might go again high. Then it can come down here. Then it can go up. This feature also can happen in AI training. It's completely random, right? So then it can come down, and finally stop at a point, right? So finally it will come to the closest point. So now the issue is we need like come down and let's say it's going up. So here is the part which is the best model so far that we have trained, which have lower loss and highest accuracy. So therefore what we do is every iteration we save the model. We train the model, we save it. Train the model, save it. Train the model, save it. Save it, save it, save it. Right? And when it's come to here, We save this model and we save this one, and this model we don't save. We check whether the accuracy is loss is lesser than the previous. Anything to a client, we give a assumption at the end saying, we assume the provided data will be in a clear and concise manner, right? Second assumption, if the data is clear and not concise enough, the time duration take for this project and the total budget for this project will change based on the data quality. These two clauses we write in all AI projects because without data we can't do anything, right? For example, a person who is giving a voice recognition model, giving me individual clips of data for each person, I can do faster training, right? It's very easy for me just to build up this neural network is the part that I have to do. But if a guy giving, okay, this is the whole meeting thing, you do the thing, how many layers work I have to do. So this requires time in AI. This is for one audio clip. Nobody is going to give one audio clip and recognition. You have to do for 1,000 people recognition. So this is going to take time. The feature engineering part is really, really important. So that's why the data scientists are paid more than machine learning engineering, because they have to get the feature extracted from that part, good quality data, right? So is that clear for you now? Why this loss function is different from you to me? Based on the loss function, your accuracy will be definitely lesser than me. How much is it? Should be less because your accuracy is less. Probably 501 mine. Test accuracy. After the training, next block. Zero point. My one is 0.501. After the training, the next block, testing the model. No, that is test loss. Accuracy 506. Yeah, your one is higher in the test node. Because why? The reason is we are splitting the training data and the testing data into random. Your testing data is completely different than my testing data. So that also matters, right? So Good, good. Right? So that depends, completely depends. All right. So therefore, no need to worry about that. So now the model have tested, even here on you will see the different percentage values because your model is different, my model is different, right? So that's totally depends. So comparison of speaker prediction and test data across the thing. Okay, let's plot the thing and see how our model actually identifies the speakers. Okay. So it will take a time. So this one. So if you read this one over here, actually this might be a little too much for you. But if you would like to learn a bit, you can. So now let's say this is the total that speech segments, right? Based on the person, Chris Wallace, Vice President, and Donald Trump. These are the speeches. So my AI model, this is the percentage value that it detected certain places as Chris Wallace. So first is really dark, that means 0.8 value. So it have detected more than 0.8. So that means it's more than sure this is the place Chris Wallace is talking. And in certain dark spot, close to 0.6, 0.3. Light mean is very less probability. And in this talk, this is definitely Donald Trump. And these dark spots are more than 0.8 places. And certain other places, it shows very late right value. So that means the AI model is not that confident enough to say this is Trump, this is thing. Similarly, that for J Trump, it has detected 100% sure this is Biden, maybe here around Biden. And these light are like maybe 0.6%, 0.56%, like that. Even in the data set, we are seeing like that. See, 0.48, 0.32, 0.19. AI model determined as Donald Trump, but the percentage is 0.48. Highest among these three. But still the accuracy is less. And if you put a threshold, it cannot detect. If you say it should be more than 70% to say this is this person voice, most of them are not clarified. Here, certain things are clarified. Most of them will not be clarified. Unknown kila tamai, it will give. Okay. So now let's say, matrix. You know the confusion matrix? So let's plot the confusion matrix. This is nothing but just plotting the confusion matrix and visualizing it. So we have tested Chris Wallace total data. So out of that data, 4095 Chris Wallace data identified as Chris Wallace data, and our AI model detected 8,802 data points as Donald Trump, which is actually Chris Wallace data point, and Chris Wallace data point is detected as Joe Biden's data point, 2,301. So here, President Donald J. Trump voice is detected as Chris Wallace, 2,170. And 14,255 is detected as Donald Trump. That is good. And 2,201 as Joe Biden. That is not good. So here, Joe Biden is detected as Chris Wallace, 12,532. Joe Biden is detected as Trump, 6,555 times. And Joe Biden is detected as Joe Biden, 5,488. That means when you upload a Joe Biden speech over there, it might say Donald Trump because it's wrongly designed for Donald Trump. See, Joe Biden detected as Joe Biden, only 5,488. Joe Biden detected as Donald Trump is more than that. Right? It's clear, right? So that's the confusion matrix. So let's clarify it with the test score accuracy as well. It's a heat map. Again, a confusion matrix with the accuracy matrix. Let's see that one. So see the percentage value, right? And the accuracy value. Precision, recall, F1 score. Donald Trump, this one 0.51, 4855. So these are the percentage metrics to visualize. So these are different visualization patterns that we do that thing. Okay. So now, as we do, we'll upload a test file and then see how our model is performing. So I'll go back to the test data and I'll drag and drop one of the test data. All the 3 test data are over here, right? That I have downloaded. Come over here. I will put it over here, right? All the 3, drag and drop, right? So now I have the test data. Go here. Where is the test data? Test 1 sample. Copy path. I'm going to put it over here, right? Then let's see how our model performs. So now it's going to break it into small pieces, right? Because it's a nanosecond based thing. So it break it into pieces. The first segment is detected as Chris Wallace. Second segment is detected as Chris Wallace. Chris Wallace, all Chris Wallace. Vice in the middle it detected as Biden, and again Chris something. So my model predicted as actually 67% Chris Wallace and 20% Vice President Joe Biden, 11% Trump. But whatever I upload is Trump voice, Obama's voice, right? So that means it didn't see, but it's maybe Obama's voice, some feature is mapping with the Chris Wallace, because we are taking a nanosecond clip. It cannot detect, right? So let's upload Biden or someone's part over here. Test 2 MP3. Let's see how it works. Trump, Biden, Wallace, all the things. Actually, again, it's detected as Wallace, but it's actually these guys who Biden speech, right? So copy path, test 3. This is Trump. It should say Trump. We'll see, because it well trained in Trump, because it detected this guy also as Trump. Let's see. Again, it's saying Chris Wallace. Maybe certain issues in the detection, our model is well trained, not well trained. But if you increase the accuracy, it might be able to tell what is the data. Okay. So maybe one more data I'll upload and see whether it's Trump or this thing. Let me check. Go to my downloads. I have it earlier. Yeah, not over here. Yeah, never mind. So like that, we can do the thing, right? So now it's clear, right? How it's working. This is CNN based model. Complicated, but you need a lot of training and everything. So the voice embedding based is the practical one, right? For if you want to add a voice to a certain person in Siri or something, the first tutorial that we have is the practical one. Why I came for this one is because I want to teach you this MEL spectrogram, right? How an audio can be trained with CNN, right? So the whole concept behind this tutorial is this MEL spectrogram, nothing else, okay? This is the person that I am interested in. Is it cool? Clear? All right. So with that note, I will conclude today's lectures. Any questions you can ask now, or else we can meet next week for speech recognition. Again, the MEL spectrogram is going to be playing a, not MEL, spectrogram is going to play a major scale. So there was another practical example. I am talking about the voice recognition. So there is certain thing, you know, the bird watchers, animal watchers, right? The animal enthusiasts, bird enthusiasts, based on the sound of a bird, they can say what that bird is looking for, whether it's hungry, whether it's scared, whether it's looking for a partner. All these things can be clarified based on the sound of the bird, right? So there was a project came. So one of our students did that project. Not everyone have that ability to understand, but a lot of people would like to go to the forest and understand what the bird is trying to say, which mood is it in, right? So what they have done is they have collected all these sounds of a bird. Let's say if it is a cuckoo bird, it collected different tones of the cuckoo bird, send it to this expert and label those sound as this is happy cuckoo bird, this is sad cuckoo bird, frustrated cuckoo bird, scared, looking for a partner, looking for food. Everything they have labeled all this sound. Now that sound is the audio clip. When they want a model, when they record a sound, it should say what mode the bird is in, right? And it should classify what bird is that. It is more or less similar to this problem that we have done. It is fixed. You are not going to add a new bird to the system every day. If you are going to select a cuckoo bird, it's cuckoo bird. You have collected thousands of data, smell spectrogram, mood data, type of the bird, mood of the thing, and what is the sound. So we have trained and it was able to perform 80% accurate, right? Based on the data provided. If they provide more data and everything, we should have training. So now when they upload the bird sound over there, it break it into pieces and it say what the mode of the bird is. Right? Like, that is one example where this voice recognition works. It classifies the voice as a bird of this bird, and it also classifies the mood. And where the other thing, these smell spectrograms are work. Sentiment. Right? How mood this guy is in. Sentiment analysis. Right? So you take the voice, put it, we can say, are you sad? Based on the voice, we can say, right? Are you sad? Yes, he's sad because the voice varies based on the mood. So the mood analysis. All these things we are going to work with this spectrogram. Right? So that's why I just introduced the spectrogram. But if you just want to do the voice recognition, this is not the standard way. CNN is not the standard way. Right? The voice library that we have used, encoding based voice recognition, that is used in mobile phones, Siri, Google Mini, whatever you name it, everyone use that type, right? Embedding based system. This is needed for certain other researchers, but I used to teach you because I can directly use now the spectrogram as an input for other things. All right, thank you so much. Then I will stop the lectures today. So we will move on. Thank you.